Okay, from today, we are going to discuss chapter 16, analysis of variance, ANOVA, right? But briefly, let me introduce you. What is ANOVA? We reviewed one sample t-test. So the null hypothesis was we had unknown population mean. It's actually we want to know what is the population mean. So initially, at the beginning, we set up a value, then we did a test, right? So the question was if it is true or not. And the next one, the pooled t-test, it is one of the independent two-sample t-test. Independent two-sample t-test. We had unknown two population means. So it is mu1 and mu2. And we want to test if they are same or not. So that was the claim, that was the question. So we had one sample, two sample, but now we have two or more sample. So that is ANOVA. So in ANOVA, the ANOVA is an analysis of variance. We are going to compare many unknown population means. So the null hypothesis will be the mu1 is equal to mu2 is equal to mu3, and we are going to have k groups. So we are compare the k unknown population means. But definitely we are going to compare k sample means, because in one sample t-test we use the x bar sample mean, one sample, so we had only one sample mean x bar. In the two sample we had x1 bar and x2 bar. But now in ANOVA, as we have a x1 bar, x2 bar, 3, even we are going to have a k sample means, because in ANOVA we have a k populations and the k samples from each. So we are going to compare the k population means. Okay, so please understand basically what we are going to do. What is the basic idea? What we want to do in ANOVA? Okay, and now here is as a copy from the textbook. It's not only in ANOVA. Is any kind of procedures. We have to do assumptions. It's a sum of assumptions. Basically, we have a random sample. Yeah, most of the sample is random. Yeah, it's basically. And the samples must be independent. When we apply the pooled t-test, is another way I said it is the independent two-sample t-test, right? So the second assumption means we have independent groups. So for example, it's a male or female, freshman, sophomore, senior, junior, senior, right? So we have to have an independent sample. And basically, as many applications assume the normal population. That means each population has the normal distribution. Yeah, as many procedures, we assume the normal populations. And the last one is equal standard deviations. You know, it is the same thing. The equal standard deviations or equal variances, that is the same thing. To remember the assumptions in the pooled t-test. You know, in the pooled t-test, we assume the sigma 1 square is equal to sigma 2 square. And I said we must assume the equal variances. It is exactly this one. The equal standard deviation or equal variance is the same thing. But now we have k populations. So it's not only between two population variances, but also we assume all k variances. Or without the square, it's all k population standard deviations. They are all same. That is the assumptions. So simply I can say ANOVA, that is the extension of the pooled t-test. In the pooled t-test, we had only two populations, but now we have a k populations, two or more populations. So I didn't assume, I assumed in only the last one in the pooled t-test, but when you read the textbook for the topic, pooled t-test, and exactly same for assumptions, yeah, we did, for even the pooled t-test, yeah. So basically you can understand the ANOVA is the extension of the pooled t-test. Yeah. So we have four kinds of assumptions, and the last one, the equal variance, equal standard deviation, it is most important. And now, please look at the picture. Please look at this picture. I mean this example. It's this one. You know, we are going to have a k populations. It's a k groups. The k can be 2. Why not? But usually we can apply the pooled t-test when we have a k equal to 2, when we have two groups. But even we have two groups, yeah, we can apply the ANOVA, because as I told you, ANOVA is an extension of the t-test. So even we have two groups, we can apply ANOVA or the pooled t-test. But later, let me show you that they will be exactly same procedures when we have two groups. Okay? So now here's the two groups. Here's a sample number 1 from the population number 1. The sample mean is equal to 20. I think is about here. Yeah, it's here. That is a 20, right? It's a sample mean is equal to 20. Let me erase. Yeah, it's like this way. It's a 20. It's a 20 here. And here is a sample number 2 from the population number 2. But the sample mean is a little bit higher. It's a 25. Maybe in the middle. It's between 20 and 30. It's a 25. So here is a x1 bar and x2 bar. When I compare the two means, there is a 5 difference. The difference is a 5. How do you think? You know, in step number 1, we can state the null hypothesis is mu1 is a mu2. The mu is the population mean. When I apply, because we didn't discuss the ANOVA yet, and now we have two groups. So let me apply the pooled t-test. Then the test statistic will be the t-score. Now then we can take the sample mean difference, and we plug the SP times 1 over n1 plus 1 over n2. You know, please focus on the numerator. We are going to take the sample mean difference. So the sample mean difference, the numerator will be negative 5. It's a negative 5 or positive 5, it doesn't matter, because the t-distribution was symmetrical. So negative t-score, positive t-score, yeah, it will be, the p-values will be exactly the same. So anyway, it's a positive 5 or negative 5. The mean difference, the sample mean difference is equal to negative 5. It's a 5, just a 5. How do you think? Can you reject the null hypothesis or fail to reject the null hypothesis? That means now I'm asking you if the difference 5 is big enough or small enough. Let me give you another example. Here is another example. It's two samples, population number 1. It's a mean equal to 20. Sample mean is equal to 20 here. It's a 20. It is another sample number 2 from the population number 2. It's a mean equal 25. Yes, it's a mean equal 25 here. It's the same sample means. Yeah, the mean difference. The mean difference. That is a 5 again. But please compare the two examples. Let me show you the two examples is together. And let me erase everything. Okay, now simply when I compare only the difference between the two sample means, example number 1, example number 2, both of them is a negative 5. It's just a 5, right? But when you look at these two distributions and these two, what can you see? You know, when we take the test statistic, it's actually the test statistic is here, the t-score. We took not only the sample mean difference, I mean not only this one, but also in the denominator. What was the name of the denominator? Standard error. We got not only the sample mean difference, but also we divided by the standard error. Standard error is kind of the standard deviation. So now in the example number 1, example number 2, in example number 1, both of them has the bigger variance, the bigger standard deviation. That means we have a bigger standard error. Please look at the sample number 2. It is very small. The variance are very small. Standard deviation, small. How do you think the standard error will be small too? You know, the standard error was in the denominator. If the denominator in the ratio, in the fraction, the denominator is decreasing or increasing. In number 1, the standard error is increasing based on the bigger variation. In the sample example number 2, the standard error is decreasing because the smaller standard deviation, right? If the standard error is decreasing in the denominator, how do you think for the t-score? when denominator is decreasing, t-score increasing. If the standard error, the denominator is increasing, then the t-score will be decreasing. Does it make sense, right? If t-score is decreasing, that means it will be getting closer to 0. You know, step number 3, I mean in the pooled t-test, in step number 3, we took the p-value. Definitely the p-value from the t-distribution. The t-distribution is the bell curve. It's like this. It's a mean equals 0. Now the t-score is decreasing. That means the t-score is getting closer to 0. What do you expect for the p-value? You know the p-value is a right end or left end probability. If the t-score is close to 0, then we can expect the p-value is increasing. I mean the area is getting bigger when t-score is getting closer to 0. P-value is increasing. What was the decision rule? If we have a very small p-value, then we reject the null hypothesis. But now, in this case, the number 1, the p-value is increasing. Definitely, we are going to have a more chance to fail to reject the null hypothesis because the p-value must be bigger than alpha. So now, step 4. More chance not to reject the null hypothesis. That means we can make the conclusion they are same. It's not only based on 20 and 25, but also using the standard error, we have more chance, is a better chance not to reject the null hypothesis. Then the conclusion will be this distribution and that distribution will be same. Let me explain to you again in example number 2. Standard error is decreasing because we had small variances. Then we can expect the t-score is increasing. T-score is increasing means the t-scores is getting bigger to the right or even getting smaller to the left. Trying to expect the p-value. Again, the p-value will be the right end or left end, but the t-score is going to the right or going to the left. What do you think? The p-value. Step number 3, the p-value is getting smaller. It's getting smaller, smaller, smaller. Finally, less than alpha. What will be the decision? Reject the null hypothesis. I can say we have a more chance to reject the null hypothesis. That means they are not same. So it's not only the t procedures, but you just compare the two distributions, this one and this one, this one and this one. It is easy to say example number 1, and they're almost the same. It's overlap, there's too much. It's almost the same. Yeah, it's almost the same. Do not reject the null statement. But please look at the example number 2. Because of the smaller variance, the overlap part is very small. Definitely, we have to make the decision, no, they are not same, right? Yeah. So, example number 1, example number 2 suggest us the same sample means, 20 and 25. But not only the sample means, but also using the variances, we can compare the two distributions, right? So please remember, when we apply the pooled t-test, we used is not only the sample mean difference, but also we use the variances. We use the standard deviations. What is the name of that? The standard error. Okay?